Have you ever stopped and wondered what's really going on inside a model like GPT when you ask it a question? Well, today we're going to pull back the curtain on the engine that powers pretty much all of modern AI, the transformer. This is the innovation that changed absolutely everything, and we're going to break it down piece by piece to see exactly how it works.
Okay, so here's our game plan. To really get what makes the Transformers so special, we have to start with the old way of doing things and why it just wasn't working. Then we'll see how a clever idea called attention started to fix things, which led to the real breakthrough, self-attention. From there, we'll put all the pieces together to build the full Transformer and see exactly why it's been such a massive game changer for the entire field.
All right, so first up, the old way and its big limits. I want you to imagine trying to read a book, but you can only look at it through a tiny straw, one single word at a time. How would you ever understand the plot? How could a machine possibly grasp the full picture like that? Well, that was the fundamental problem they were trying to solve.
So these older models, you might have heard of them. They're called recurrent neural networks, or RNNs. They read sequentially, just like it says. They process the first word, create a little summary of it, and then pass that summary, or memory, on to the next word. It's kind of like that game of telephone you played as a kid. You pass the message down the line and just hope that the meaning isn't a total mess by the time it gets to the end. And that game of telephone leads directly to this, what we call the bottleneck problem. By the time the model gets to the very last word, that one final bit of memory has to somehow contain the meaning of the entire sentence. Now, for a three-word phrase, maybe that's fine. But what about a long, complicated paragraph? There's just no way. It's too much information to squeeze through one tiny little opening. So how do you solve a problem like that? Well, the first big attempt was a really clever mechanism called attention. It was designed to fix that bottleneck, but in doing so, it accidentally revealed an even deeper, more fundamental flaw in how they were thinking about the whole thing. The basic idea behind this vanilla attention was pretty smart. Instead of just relying on that one final memory state, what if at every single step, the model could look back at all the original words from the input? This gave it direct connections to everything, completely bypassing the bottleneck. Now it could pull context from anywhere it needed. Seemed like a perfect fix, or so it seemed.
And this is where the big revolutionary question came up. Wait a minute. If the model can instantly access any word from the input, whenever it wants, why are we still forcing it to read sequentially, one by one by one? It turned out the real bottleneck wasn't just the memory, it was the entire one word at a time process itself.
And that brings us to the huge turning point. This is the absolute core idea behind the Transformer. What if you could just get rid of that one-by-one processing entirely? What if every word could look at every other word, all at once? That's exactly what a new mechanism called self-attention was designed to do.
This was the fundamental aha moment. If attention already gives every part of a sentence access to every other part, why do we even need those slow, sequential links connecting them in a chain? And the answer was simple. We don't. We can just throw them out completely.
And that, my friends, is self-attention. It's a system where you don't have a straight line anymore. You have a web. Every single word can now look at every other word in the sentence at the exact same time. This was a total game changer because it meant you could process everything in parallel, making things unbelievably faster.
Okay, so how does this magic actually work? The best way to think about it is like a tiny, super fast search engine running inside the model. For every single word, the model creates three things: a query, a key, and a value. The query is basically the word asking a question, like, hey, who here is relevant to me? The keys are like little labels on all the other words, shouting, this is what I'm about. And the values? That's the actual stuff, the meaning of those other words. So it works in 4 quick steps. First, for every word, we generate those query, key, and value vectors. Then, one word's query compares itself to every other word's key to get a score. Think of it like a relevant score. Third, we take all those scores and turn them into weights, which basically decide how much attention to pay to each word. And finally, we just take a weighted sum of all the values and boom, you have a brand new, super context-aware version of your original word. Now, that whole process is incredibly powerful all on its own. But the real magic happens when you realize maybe just one perspective on a sentence isn't quite enough to really truly understand it. And this is where multi-head attention comes in. The idea is brilliant in its simplicity. Instead of running that whole self-attention process just once, Why not run it, say, 8 or 12 times, all in parallel? Each one of those parallel processes gets its own set of query key and value calculators, and each one is called an attention head.
So why do this? Well, think of it like having a team of different specialists all analyzing the same sentence. Each head can learn to look for different things. Maybe one becomes an expert in grammar. Another one gets really good at tracking who did what to whom. A third head could focus on identifying pronouns and what they refer to. Together, they build this incredibly rich, multifaceted understanding of the text that a single head just couldn't. Okay, so after all those attention heads have gone out and gathered this amazing, rich context for every word, what happens next? The model has to actually think about it all, right? That's the job of the feed-forward network. After all that information mixing between words, this is a little processing station for each word individually. It takes that new context-rich version of the word and does some calculations on it, getting it ready for whatever comes next.
So, now we've got all our parts. We have self-attention to gather context, multi-head attention to get different viewpoints, and feed-forward networks to actually process it all. So let's put it all together and see how we assemble the complete transformer block, the fundamental Lego brick of today's giant language models.
The full architecture actually has two main halves that work together. On one side, you've got the encoder. Its job is pretty simple. Just read and understand the input sentence using all that self-attention stuff we've been talking about. On the other side, you have the decoder, and its job is to generate the output sentence. The decoder is a bit more complex, though, because it has a couple of extra tricks up its sleeve: masked self-attention and something called cross-attention.
So what's this masking all about? Well, think about it. When a model is generating a new sentence, it can't be allowed to cheat by looking at the words it hasn't even written yet. Masked self-attention is just a simple trick that basically puts blinders on the model. It prevents it from seeing any future words in the sentence, forcing it to make predictions based only on what it's written so far. No cheating allowed.
The other key piece is cross-attention, and this is the vital bridge that connects the two halves of the model. It works just like self-attention, but with one major twist. The decoder creates the query to ask a question, but the keys and values it gets to look at come from the encoder. This is how, say, a translation model can constantly look back at the original German sentence to make sure its English translation is staying on track. It's absolutely crucial. So, there we have it. We've built the transformer. But why? Why was this specific combination of ideas the spark that lit the fuse of the entire AI revolution we're seeing today? What made it so much better than everything that came before it?
Well, it really boils down to three superpowers. First, massive parallelization. By getting rid of that one word at a time process, you can train these models on huge amounts of data way, way faster. Second, they're amazing at understanding long-range context. The first word in a giant document can talk directly to the last word. No problem. The bottleneck is gone. And third, they're stackable. These blocks are like Legos. You can just pile them on top of each other to create deeper, more powerful models. And that idea of stackability is absolutely key. It's not just a theory. The original transformer base model, the one that started this whole revolution, used a stack of 6 encoders and 6 decoders. Just 6. That was mind-blowing at the time. But today's models, they stack hundreds of these layers. It's a design that just scales beautifully. And this really brings us to our final thought. The transformer gave machines the incredible ability to see the context of the entire forest and the details of every single leaf on every tree, all at the same time. Now that this fundamental barrier has been completely shattered, the real question is, what's the next frontier for artificial understanding?